part of our section 9.1, looking at other types of sequences, we're going to talk about recursive sequences. Now, recursive sequences are very time consuming because unlike your normal sequence, say if I wanted to find the 20th term of a sequence, we used to be able to just take 20, plug it in for n, crunch the numbers, and you have that value for the 20th term. A recursive sequence is much different. You're going to have to find all the terms 1 through 19 before you can find the 20th term, because the 20th term is probably going to depend on 2 or more terms before it. So example 13 says find the first 7 terms of a sequence. Now, a dead giveaway for a recursive sequence is you will not see n at the base level. You will see sequence functions with subscripts. That's where your n's are located. So this is 2 times a sub n minus 2 plus a sub n minus 1. And another giveaway is that they're going to predetermine or define some terms. So the first term is 5, second term is 6. So to find the third term, that means n is 3. So we're looking for a sub 3, which is now 2 times a sub 3 minus 2, which will be a sub 1, and a plus a sub 3 minus 1, which will be a sub 2. So bring in the 5, that's the first term, bring in the second term, crunch the numbers, 2 times 5 plus 6 is 16. There's the third term. Okay, I get it, I see it now. I have to take, if I want the third term, I got to go back 2 terms, multiply this by 5, add the 6, and I get this term. So to find this term, I got to go back 2 terms to the 6, multiply it by 2, and add the 16. Okay, that's 28. Fill it in. So once you find this pattern, it helps speed things up. To find this blank, jump back 2 terms to 16, multiplied by 2, add the 28. That's a 60. To find the next term, jump back to 28, multiply it by 2, add the 60. That's 116. To find our last blank, go back 2 terms to 60, multiply it by 2, add 116 is 238. 236. Or if you look at how everything's written out, you can see that once you're done and you multiply the 5 by 2, you throw it out, you replace it with the 6, and you move the 16 over. That's 28. Oust out the 6, put in 16, move over the 28. Take out the 16, move in the 28, move over the 60. Out goes 28, in comes the 60, then the 116. So you can also see that pattern that way. Another special type of recursive sequence is Fibonacci sequence, which is basically defined as adding the 2 previous terms, starting with 3 as n, and the first 2 terms are 1. So 1 plus 1 is 2. 1 plus 2 is 3. 2 plus 3, 5. 3 plus 5, 8. 5 plus 8, 13, and so on and so on and so forth. That's a famous recursive sequence. Another special sequence we're going to look at are factorials. You see this n exclamation point. That means either 1 times 2 times 3 times 4 times all the way out to the n, or you can do it backwards, n times n minus 1 times all the way down to 1. I prefer the one in red, especially when it comes to simplifying. It makes your work a lot easier. We do have a special case that 0 factorial does equal 1. And some people say that 1 factorial is a special case, but in all reality, okay, if I start counting at 1, I'm already there. So that's my answer, 1. All right, simplifying. As I said, we don't want to use what's in blue because I don't want to write out 1 through 23 on the top, 1 through 19 on the bottom, just to cancel out all the 1s, the 2s, the 3s, the 4s, the 5s, the 6s. I would prefer to start backwards. To start with 23 times 22 times 21 times 20 times 19. Once you get to 19 and it's a match to the bottom, call it a factorial. Then you can just cancel those instead of canceling out 19 pairs. Multiply the 4 numbers together, you get 212,520. So if you go to your calculator, just to quickly show you where the factorial button is on your calculator, and type in just what you see. So I'm going to go alpha y equals, get a fraction, type in my 23. Now the factorial button's underneath the math button, and you want to go over to probability. 1, 2, 3. Choice number 4 is your factorial. And then we can put in 19, math, and if you don't want to go across, you can also go to the left. and then type in a 4, hit enter, and there's my answer. So that's how you use the factorial button on the calculator. If they give us variable expressions, same concept. Start with n plus 2. Subtract 1 from the constant makes it n plus 1. Subtract 1 makes it n. Oh, that matches my denominator. Cancel them out. There's my answer. If I have 2n plus 2 factorial over 2n factorial, okay, so I need to count backwards. Start with 2n plus 2. Subtract 1 from this 2, not the 2n, just here. 2n plus 1. Subtract 1 gives you 2n, so these 2n factorials, they should be in parentheses, but they're a match. You cancel them out. There's my answer. So which grows faster, factorials or exponentials? So let's let k be our base. So 2 to the n is 2 times 2 times 2 times 2 times 2 all the way up to 2 to the n. And factorial would be 1 times 2 times 3 times 4 times 5. And if you look at the first 3 terms, 2 times 2 times 2 is 8. 1 times 2 times 3 is 6. This is bigger, but as soon as you get to that fourth 2, that's 16, and 6 times 4 is 24, now my factorial is bigger. Because at this point, I'm always multiplying by a bigger value than what's being multiplied up here. So factorials will always increase faster than an exponential. And it doesn't matter if your base is 100. Eventually, I'm going to go past 100 in my factorial. So for once n is greater than 4, 2 to the n is less than n factorial. So factorials grow faster. So if I was doing a limit where n approaches infinity and I have 2 to the n power over n factorial, because I just showed that this grows faster, our limit's going to be 0. So again, k can be any base. It doesn't matter. You will still have a limit of 0. If I switched and put the factorial on the top because this grows faster, then we are going to infinity, and that diverges, and we can say that the limit doesn't exist. We're heading to infinity. Okay? So that wraps up 9.1.